Welcome to the ePathshala lecture series on computer science for postgraduate students. We are dealing with the subject computer graphics and visualization. We had 12 sessions in this lecture series. This is the 13th session where we will be continuing from where we have left in the previous session. We were talking about B-Splines, the base is splines, and it is the quadratic B-Splines. We talked about linear B-Splines where the order m is equal to 2, and if the order m is equal to 3, we will get quadratic B-Splines. If the order m is equal to 4, we get cubic B-Splines, and so on. So B-Splines are more generic, and the blending functions that make up the B-Spline can be generated by using Cox-de-Boer recurrence relations. The Cox-de-Boer recurrence relations have been given in the previous session. You can recollect the equations. And if that is the n k comma m of t is a blending function of order m, and it is kth B-spline blending function, because the order 1 B-spline blending function has to be defined. We have defined it like this: n k comma 1 of t is equal to 1 if tk less than or equal to t less than or equal to tk plus 1 is equal to 0 otherwise. So we have chosen the not vector to be uniform. Okay, uniform here in the sense a not vector is basically the values of the parameter t, where the blending functions actually meet, or blending function start, blending function ends, and these values are the not values, and they are always increasing. You can recollect the discussion in the previous class for you to better understand this session today. So let us continue with the next, that is quadratic B-splines where m is equal to 3. So let us do that, and later we will discuss the other types like the constructive solid geometry mechanisms, sweep representations, and fractals, and with that we will be concluding the 3D object representations part. So let us continue the discussion of splines with B-splines with the quadratic B-splines. So quadratic B-splines are built on again a uniform not vector where the not values t0, t1, t2, t3 are uniformly placed, and the m is 3. You should remember every B-spline blending function is associated with one control point. So for example, say in this slide here we have shown here in 4 colors, so that means we have assumed 4 control points. Each control point is associated with one blending function. That means p0 into n0 comma 3 of t, p1 n1 comma 3 of t, p2 n2 comma 3 of t, and so on. So n k comma 3, k is here 0, 1, 2, 3, and so on. As many control points, those many blending functions. Using the Cox-de-Boer recurrence relations for m is equal to 3, the first B-spline blending function n0 comma 3 of t can be derived with the equation of Cox-de-Boer recurrence relation. As we know from the recurrence relation that the recursive equation that a B-spline blending function of order 3 can be derived from 2 B-spline blending functions of order 2. So 3 minus 1, 3 minus 1. So using that we can formulate this equation. As we did with linear B-splines, we can take the first case where t is assumed to be between 0 and 1, and n0 comma 3 of t is equal to t squared by 2. As from this we can derive, you can do the derivation for yourself, take your time, and refer to the equations like the first order B-spline blending function equation and the Cox-de-Boer equations. You will be able to derive this. So when we derive this, we get nice flowing curves which are quadratic because the degree of the parameter is 2, and n0 comma 3 of t starts at 0 and ends at 3, n1 comma 3 of t starts at 1 and ends at 3, and so on. So from this we can formulate finally the n0 comma, the first B-spline blending function can be derived with the equations as shown here for various intervals of t, and n1 comma 3 of t, because it is shifted by 1 unit to the right as per the as per this diagram, n0 comma 3 of t starts at 0, ends at 3, n1 comma 3 of t starts at 1 and ends at 4 and has the same shape. So, what we can say is it is just shifted by 1 unit to the right. So, you do not have to do again a derivation as we did for n 0 comma 3 of t, rather we can instead we can replace t with t minus 1, you get wherever there is t, replace that with t minus 1, you get n 1 comma 3 of t equations. Similarly, if you want to get n 2 comma 3 of t, replace t with t minus 2 and you get equations and so on. So, you do not have to do a derivation further. So, if we see the properties of the B-splines, as we had seen the properties of Bezier curves, similarly we have got properties of B-splines. They are also well behaved, they also sum up to unity, the blending functions that define the B-splines sum up to unity for every t, and they are more generic in nature. That means the knot vector, even if it is uniform knot vector that we have considered, we can derive Beziers from B-spline. So, they are more generic, as we will see further in the properties. So, the first property says that the mth order B-spline blending function is a piecewise polynomial function of order m and is smooth enough. So, the continuity levels that it shows is C m minus 2. If m is 4, it will show second order continuity, m is 5, it will show third order continuity, and so on. So, convex hull property is another important property which is similar to the Bezier curves, and the B-spline curves also satisfy the same property. And the B-spline blending function n k comma m of t starts at t k, that is n 0 comma 3 of t starts at 0, ends at 3 and so on. So, and ends at t k plus 1, ends at t k plus 1, that is n 0 comma 1 of t starts at t 0 and ends at t 1, and so on. So, its support is t k. Support here is the interval in which the function is non-zero. Okay. The range of the parameter t is divided among a total of L plus m knots. Here the number of knots can be calculated by L plus m as the number of knots. The order, one important observation, and one it should never happen that the order should never be less than the number of control points, or can be just equal, but should never, but it is always equal to or less than, it is always equal to or less than the number of control points. L plus 1 are the control points. The order should never exceed the number of control points. It should be, order here is if number of control points are 8, order can be 6 or 7 or whatever can be, but it can never exceed the number 8. So, each curve segment, an important point to understand the local control property, each curve segment is affected by m minus 1 control points. That means, if the order that we are using for the curves is say 3, that is we get quadratic curves, and we can observe that 2 control points will be affecting a curve segment. That is, a section of the curve is affected by or is influenced by 2 control points. And another property, any one control point can affect the shape of almost m minus 1 curve sections. So, that means if the order is 3, a control point will affect 2 curve sections. So, that is its indication. So, it is important that a control point will not be affecting the whole of the curve. So, unlike the Beziers, here a control point will be affecting only a limited part of the curve. So, that is where we achieve local control. So, if we shift that control point, only that section influenced by this control point only gets altered. So, that is the meaning of it. And if standard knot vector is used, again we have a new word here, standard knot vector. If standard knot vector is used, B-splines will interpolate the first and last control points. So far, B-splines on uniform knot vector, if you remember, the uniform knot vector is where T0 is 0, T1 is 1, T2 is 2, the knots are uniformly spaced. While a standard knot vector is where there are multiple knots. When there are multiple knots, we get a standard knot vector. What is multiple knots? That means, if at one knot value, if we have more than one knot value at a given position, we call it a multiple knot. What happens if there is a multiple knot? And you can refer to this slide. Now, when the knot values, when there are multiple knots at a given position on the parameter interval on this parameter axis, what we get is a multiple knot, and we get what is called standard knot vector. That knot vector in which some knots or multiple knots is called a standard knot vector. You see this here, T is a knot vector with multiple knots for 0 and multiple knots for 5, and there are no multiple knots for these 1, 2, 3, 4 are not multiple, they are ordinary knots. So 5 is a multiple knot of multiplicity 4, and 0 is a multiple knot of multiplicity 4, because the number of times that the knot repeats, the same knot repeats, is 4 times. So this discussion, I think you can refer to this, you will easily understand. The important point here is, if you use this standard knot vector, you can generate Bezier curves using the Cox-de-Boer recurrence relations on standard knot vector. If you use standard knot vector and if you use that is Cox-de-Boer recurrence relations, what you get is actually Bezier curves, that is the Bezier blending functions. So we can further move to the next. With this we will be ending the splines part, and maybe we will be moving further to the next 3D object representation mechanisms, which are sweep representations, constructive solid geometry, and fractals. Let us see what is the sweep representation. A sweep is something like you can have translational sweep or rotation. How do you create a 3D object from a 2D object? That is the essence of it. So take a 2D object. What you can do is, imagine you have to create a hose pipe. What is that you do is take a circle is a 2D object, and define a path. Path is again 2D shape, that is you define a curve. So for the hose pipe, and if you trace the circle and along this path, what you get is a hose pipe like. So that is how we can create 3D objects using 2D objects. Similarly, that is called translational sweep. Translation is basically if you use an exact straight line. So if you want to create a tube like object, a perfect cylinder like object, take a circle and draw a direction perpendicular to the cylinder for some height, and you trace the shape of the circle till that height, what you get is a perfect cylinder. So that is translational sweep. A rotational sweep is where, imagine you have to create a torus like shape, or you have to create a bottle like shape. What is that you can do is, you can take a circle or you can take the shape, like say for example you can take a shape like this, and you imagine an axis, rotate the shape about this axis is vertical, rotate the shape about the axis and rotate for 360 degrees, and what you get is rotational sweep, and the trace produced is actually a 3D object. So if you take a circle like 2D shape and rotate it about an axis, what you get is a torus like shape as shown here in the slide. If you want to get a bottle like shape, you can rotate the line, the boundary line of that, and rotate it about an axis for 360 degrees, and what you get is a bottle like. So that you can create such 3D shapes from 2D shapes. Again, another technique to create 3D objects or to represent them is constructive solid geometry, which is also called CSG, where we apply Boolean operations on regular standard objects and get complex objects. Like for example, Boolean operations are union, intersection, and subtraction. So A union B, A intersection B, and A minus B, like things you can use. Intersection, union, subtraction. If you can look into the slide, there are nice shapes shown here. One is a cube, the other one is a sphere. The cube and sphere, when you have to say A minus B, you have the second shape. When you have A intersection B, you have the third shape. Okay. So you can see how various complex shapes can be produced by combining standard objects, 3D objects. That is what is called Boolean operations, and this technique is called constructive solid geometry technique. This is constructive solid geometry, and how do we implement this? How do we apply Boolean operations on constructive solid geometry? Based on this we can apply techniques like ray casting and ray tracing are the most fantastic techniques which can be used to implement constructive solid geometry. Ray casting is where we imagine that we have got a light source. Say for example, we have got a light source. We have got, say, a series of objects, maybe a collection of objects in the 3D world. Imagine a plane onto which we want to actually apply this, that is identify the Boolean, intersection, union and so on. The Boolean operations are to be performed. So now we will be in ray casting. What we will be doing is we will be tracking, will be starting from what is called a pixel position, and we will be firing a ray perpendicular to the pixel position into the 3D world. It hits various objects and it emanates, because if they are transparent objects it emanates, if they are opaque objects it hits, and further it takes other directions and so on. But anyway, all the light finally, all these rays finally reach the light source. Imagine that there is a light source, and now many rays fall onto this, many rays spread in various directions, and not all these rays pass through this rectangular grid here as shown in the picture. As shown in the picture here, not all the rays from the light source pass through this grid. Only few light sources pass through this grid. So how do we know that which light sources pass through this grid? So what we do is, instead of starting from the light source and tracing a ray, will be starting from the grid here from one pixel position, and we will be tracking the ray in the reverse order towards the light source. That is what is the principle used in ray casting. So fire a ray from the pixel position, from every pixel position take the first pixel position and fire a ray, and then reach the light source, and by tracing the ray. So like this we can apply union, intersection. As you can see here in the second diagram, there are two objects, and when a ray is fired, it hits object, the first sphere at A and at B at two positions, and object 2 at C and D, and maybe you can now apply union, intersection, difference and so on. That is called constructive solid geometry. The next representation is QuadriOctree and Octree representation for a solid object. So far we have talked about only surface modeling in splines, in mesh modeling. Now as you can recollect the discussion on the beginning of 3D object representations, we talked about solid modeling, that is how to model the inside of an object. So we can use a different representation for modeling the inside of the object. Like for example, if you take MRI scans, the 3D scans or MRI CT scans, where you not only take the outer shell of the human part, but also the inside of it, because some tumor is there, we have to identify, we model the inside of it also. So how to model the inside of it is using techniques like BSP tree or QuadriOctree, binary space partitioning trees and so on. So let us see how the data structure corresponds to an octree. Before that we can go to QuadriOctree and understand. QuadriOctree is basically take a region of space, divide that into 4 quadrants, take a region of space, divide that into 4 quadrants, identify the homogeneous regions. If there is any non-homogeneous region, divide that further. So divide again that into 4 quadrants. So imagine if this, assume this 2 is the non-homogeneous region, divide this into again 4 quadrants. Again if you found that one of these quadrants is non-homogeneous, divide that further. So keep dividing further till all the regions are homogeneous. That is how a quadtree is represented, and this is the data structure. And the extension of it is octree, where each element is a voxel. Instead of pixel we use volume pixels. So volume pixels are, in short, it is voxels or volume pixels. And if you use a volume, again we follow the same analogy, that is consider a volume of space, not a region of space, consider a volume of space, divide this volume of space into octants, that is 8 portions or 8 pieces. So take a cube, 8 pieces, and find out all the non-homogeneous volume pieces, and they divide them further into 8 more pieces, and keep dividing them further into till the regions are homogeneous. That is one way of representation. One another way is BSP trees, or binary space partitioning trees. These are examples for solid modeling. So, the octree example for solid modeling, BSP trees are examples for solid modeling, where divide the space, entire space into make a binary tree, that is divide this into two parts by a dividing plane. For example, see this 2D division, take a region of space, divide that using a boundary plane or a plane. So, is a line here, in 3D it will be a plane. So, it divides the space A into B and C, and B is divided further into D and E, and that is how you form a binary tree here. The extension of that is in 3D, where the region of volume of space, that is this entire 3D space, is divided using a plane into two halves, and again inside that into two halves, and again each the volume into two halves, and you form a binary tree. It is called binary space partitioning is the method here. And lastly, fractals. Fractals are a peculiar because we wanted to model various objects in the world, but why do we have splines, why do we have meshes, why do we go for what is called CSG, why do we need to go for all these when we can do with get away with splines or NURBS? Why do we go with all these is there are splines cannot model every object in the world, or some objects are such that we cannot just like that model, or maybe easily we can model with tools like meshes or splines or NURBS. We will have to go for tools like fractals. For example, fractals are fantastic to model trees or leaves of trees or trees, coastlines, clouds, terrains, and these are what fractals can be used to model. Fractals are procedural objects, unlike so that is you can repeat the procedure infinitely to get many objects. Fractals repeat themselves infinitely, and as I mentioned, you can use it for modeling terrain, plants, clouds, water, fur, and so on. Fractals are basically a copy of it, so that is the smaller parts of it look exactly similar to a bigger part. A smaller part, that is if you take an object, if you take the smallest part of it, its shape is exactly the same as the biggest part. That means we call it, they are called self similar fractals. The scaled, so a small part is actually a scaled down version of the big original complete whole. So, take the whole, reduce it in size. So, it is a small part is actually an exact replica of the whole. It is similar to forming many, taking many smaller shapes and giving the same shape as a big shape. So, that is how it is. One best example in the real life for a fractal object, you can, all of us have seen that object. You can try to recollect any shape. So, all of us have seen this fractal object in our day to day life, that is your cauliflower. So, cauliflower is a vegetable. It's you cut it to any down any size, any smaller size, the smallest piece still looks like the big cauliflower. It has the exact shape, but only it is a scaled down version of the original cauliflower. So, cauliflower is the best example for a fractal. Now, you can so that you can relate when we have discussions on fractals. Some of the nice shapes of fractals is that the dimension of fractal is one important thing that we can talk about. Lines have one dimension, areas have two dimensions, and the volumes have three dimensions, but whereas fractal objects have dimensions like 1.5D and so on. So, fractals somewhere fall between 1D and 2D. So, their dimensions fall between 1 and 2. So, that is quite interesting. And examples of fractal is this. What is that you can do is take an initiator and take a generator. So, initiator is some initial shape like a triangle. What you can do is a generator, that is replace every straight line in the shape, initial shape, with make it into 4 parts, replace the middle part with a spike. See this here, take one line, divide that into 3 parts, replace the middle part with a spike, and whose edges have the same length as that of the other, that is the the three parts we made it, okay, each part. So replace the middle part with a spike. So if you keep that is the first generation we call it, and now again repeat this infinitely. Say take every edge, divide that into three parts, replace the middle with a spike, and if we keep doing this is the second generation, and if we repeat the same procedure again and again, we get the third generation. Like this, to a surprise, if we keep doing this, then this and this, the length of the fractal will be increasing enormously in dimension, but its space will remain fixed. That is, the region to which it is contained in is remains fixed. So it won't go beyond. Its length keeps increasing, but still its dimension or its area of a spread, its spread remains constrained to one small region. That's the beauty of fractals. This is an ice flake. The shape is called an ice flake. This is called Koch curve. So famous scientist Koch has a Koch curve, which is a snowflake. It's a snowflake curve. So fractals are so fantastic in modeling clouds, terrains, and so on. So with that, we come to the end of the discussion, and with particle systems is one thing that is used to model particles like fire, like raindrops, like fog, mist, and so on. So explosions and so on. So with that, we come to the end of the discussion on object representations using we started with mesh models, then we continued with splines, then we discussed about CSG using constructive solid geometry. We have used fractals, we have seen fractals, we have used sweep representations, we have used octrees and BSP trees. So a lot of discussion is there in many books, and you can read more into books, so for more understanding. For further, if you want to know, you can do this. With this we come to the end of this discussion on 3D object representations. Thank you.